So when I say that you have an ODE, first order ODE, it's associated with one parameter group, local. Something is invariant, it means it's invariant. It means I take the orbit and the function stays constant on it. Okay? Or the level of the vector field. The vector field kills the function you're discussing. It's constant. Now, this is an easy thing that you can compute, but it must be obvious. It must be obvious that this norm is invariant by the action that defines geodesics. Right? I mean, it must be somehow obvious. And I do not know a direct proof. I only know this proof by calculation. I want to think of a better proof before I lecture. I know that this can be proved conceptually. I will show you now and later this afternoon that this is conceptually obvious. But I don't know a direct proof of that fact. Strange. Okay? Now, that was the Lagrangian point of view toward geodesics. And the fact that these two differential equations are the same says the Lagrangian point of view and the Levi-Civita point of view is the same, remarkably enough. And Levi-Civita is good for indefinite metrics and so on, so somehow Levi-Civita is better, right? Let me start the second part of this. So, Hamiltonian point of view. Let me write. I'll let my physics friends make fun of me to tell me how stupid I am. I'll give you all physics people a chance to do how stupid I am. Momentum that's a physics word. I'll gamble on it. I worry about the numbers because every physicist has really precise numbers in his head about what is what. Am I close? M is mass, V is velocity. Do I need a constant in front of this? A half or something? That's okay?
Yes.
Got it? You agree?
Still much space between equal and M.
Yeah, I left the space here for a constant. Okay? Momentum is equal to mass times velocity. It makes sense, right? If a huge train is going at some velocity, right, and hits a wall, and it goes at the same velocity I am, I mean, you know, I'm huge, but the train is huger, and there's more momentum and so on. It's mass times velocity. Then, as a mathematician, you look at that equation, and you say that's interesting. Velocity in a manifold goes in various directions. Right? We're talking about velocity vectors along a curve. Right? So maybe this mass, maybe this is a linear function of velocity. By the way, another physics word for momentum, by the way, in German is impulse. Right? It's the same word, right? Impulse, same. In German, it's impulse. Right? You don't like this word? You don't know this word?
That's like
I-M-P-U-S. Huh?
something else included.
What?
But it's the same moment. Yeah, okay.
Up to some constant, I'm sure it's the same thing. Mathematician, if you don't regard this thing as being important, you've lost a huge amount of deep thinking by serious colleagues in physics. Well, that's interesting. By the way, the standard letter for momentum is P. Do you agree? Get used to it, mathematicians. The standard letter for momentum is P. Momentum is a linear function, so P is a linear function of velocity. So this means if I go from velocity in the tangent bundle, whatever that means, I should go to momentum in the cotangent bundle. Right? Because fiber-wise, a velocity vector in one fiber is associated, maybe if I write m times v, a linear function. So Newton and probably Archimedes probably knew that momentum equals mv. I mean, there must be a way of Galileo for sure. I mean, these people really knew about momentum. Momentum is a linear function of velocity. So we should understand how to go from a linear function of velocity to momentum. Well, the word you want to put here is Lagrange. Because we had the Lagrangian and talked about a Lagrangian theory and all of this stuff here. And the word, famous name you want to put here is Hamilton. Now, mathematicians have heard of the name of Hamilton, but probably only because he discovered, that people say he discovered the quaternions. That is more or less trivial discovery in my mind. Psychologically, it's maybe not trivial, but mathematically it's a trivial, you know the quaternions are some trivial thing. And there was a long search for such a division algebra and so on, but that is not Hamilton's main contribution. He did a lot. And what I'm talking about here is really fundamental, in my mind, far more fundamental than any little quantum. So we have what we call here Lagrangian mechanics. And what we have here is Hamiltonian mechanics. So Lagrangian mechanics and Hamiltonian mechanics. And it's the same. And the Hamiltonian viewpoint is, in my opinion, very much more powerful. So this connection here, in the sense of how to go from one place to another, is called the Legendre transformation. I don't know the history well enough, but he had very close contact with Lagrange. And you will see in this, I will talk about the Legendre transformation in a minute, well, next lecture. But you will see that it's the beginning of Lagrange multipliers. You know this method of Lagrange multipliers for finding critical points, functions restricted to certain submanifolds. So this Legendre transform takes this thing from the tangent bundle to the cotangent bundle. And then we will see that the key fact that you will see in the next thing, fact that we will use, is that the cotangent bundle has canonical symplectic structure. Whatever that means, there is a canonical thing going on here that we can use that will tell us a great deal about the geometry of geodesics. Okay? Let's stop here, make a break of, how long should we break? What do you like? 10 minutes, 15 minutes? Is 15 afterwards too much of a break? You're not exhausted by me? Well, how about take a 10-minute break? 10 after. Okay? Great, thanks.